Okay, so far we have discussed how the reactive power, voltage, and the active power are related, and then we have also seen how different components in the power system contribute to the reactive power and the voltage, right? So let's now with the all that knowledge in hand, let's talk about the different method of voltage control, right? So basically, you can categorize the voltage control methods into two types. One is the by using the tap changing transformers, and the other method is injection of reactive power. Okay. So let's first look at the how we can utilize the tap changing transformers to control the voltage. Right. Mm, right. Uh, as you may already know, the what we are doing here is we are basically changing the turns ratio to control the voltage. So the voltage control is voltage is controlled by changing the turns ratio, right, of the transformer. So this operation is called the tap changing, and there are two types of tap changing transformers sorry about that available. One is called the offload uh, tap changing transformers, and the other one is called the on-load tap changing transformers, right? So uh, so as the name said, the offload tap changing transformers, so they basically need to disconnect from the load during the tap changing operation, right? uh, but so right, but on-load tap changing transformers, as the name says, they don't need to be disconnected, so they can operate while the load is connected, right? So how it is happening, so if you draw the arrangement, so you have the line, and then you have the winding, and there are then right, so two resistance, and there's a switch S1 here, and there's another switch S2 here, right? and then there is this arrangement to change the taps. So you have the winding, and from the windings you have the taps. Okay. So these are the taps, and then you have this two tap changing arrangement where you can basically change from one tab to the other, right? So let's call this one B and this one C, right? So you basically, these are called the selector switch, right? So during the tab changing operations, this is what will happen. Okay, I should okay, let me try to write it here so it will be clear. So during the operation, right, so what will happen is S1 opens, right? So the S1 get open, so the total the total current will go through the other path, right? So the say the current flows through S2, right? So still the connection is there, the current is flowing, and then the selector switch B changes the tab, right? Right, so it will change the tab because there's no current going on here, so the tab can be changed. It change the tab, and then S1 will close. Right. So then when that happens, there will be a circulating current in the right, in this loop, right? So what we will have is the circulating current flows in R superimposed loop, right? And then so then what you do is the S2 will open, okay, and C will move to next tab, right? Because there's circulating current because in this loop here, and then the S2 will open and move to the tab, and then the S2 will close, so they will be at the same tab, so there won't be any circulating current and the current will flow to the load, right? So so you can see that now without disconnecting the load, you can change the tab in this situation, right? Okay, so let's consider the radial transmission system with two tap changing transformer, right? So radial transmission system with two tap changing transformers, right? So let's say you have offload tap changer, so something like this. So you have the tabs, and tabs are taken like that, and then you have the selector switch, right? So let's say the IS current flows from the source side, and then the ratio of the transformer is 1 to TS, and then you have the transmission line R plus JX, and the other end also you have a tap changing transformer with the number of taps. So let's say this is the receiving end. So you have IR current going through the load like that. So let's say this voltage is V2, this voltage is V1, and here you say we have VS, we supply, and we receive voltage, right? And let's say this trans ratio is TR to 1, right? So the TS and TR are fractions of nominal transformer turns ratio. Okay. So now we need to determine the tap changing ratio to completely compensate the voltage drop in this line, right? So we will now the task is to determine the tap ratios to make the voltage drop across the line to 0, right? So let's consider the product of TS times TR. We will make it unity, right? So that will be equals to 1. So you have TS times TR equals to 1, right? So that the overall voltage level remains in the same order, and minimize the range of tap on both the transformer used, right? So we can do the impedance transform in here, and transform this R plus JX to the receiving end. I will take a copy of this and do that. Oops. Copy and paste, and I will scale down a little bit. and then basically, oops, okay, I change this impedance to the other side. So you will have something like this. This whole thing we will move, and so we will have R plus Jx over TR squared in here, right? And then this will become actually, so this Vs is actually equals to the V1 over Ts, and then here we will call this Vx, that would be equals to Vr over Tr from our turns ratio. So now with that we can write that Vs is equals to V1 Ts and Vr is equals to actually yeah, this should be V1 Ts because the turns ratios that we had, but this would be Vr over Tr. So Vr here is actually Vx times Tr. And so from here we can from this we can write that the Vs is equals to Vr, which is equals to V1 Ts, and our Vx is equals to Vr over Tr from here, which would be equals to, since this Vr is equals to V1 over Ts, this would be equals to this, right? And so we can calculate the voltage drop, right? So we will say arithmetic or the calculated voltage drop, it will be equals to V1 Ts over Tr minus V2, right? That is Vx minus V2, approximately equals to Rp plus Xq over Tr squared V2, right? And as Tr times Ts is equal to 1, we can say Tr is equals to 1 over Ts. So we have V1 Ts squared minus V2 is equals to R times P plus X times Q over V2 times Ts squared, right? So So we have equations like this in terms of voltage and the turns ratios. Mm, we can arrange. I'm doing some couple of steps at the same time. So multiplying by v2 everything and just in this one, so v2 squared uh, plus v2 squared minus ts squared v1 times v2 plus rp plus xq ts squared would be equals to 0. So you have a quadratic equation here. So we can solve for v2 is equals to half ts squared v1 plus or minus ts square root of ts squared v1 squared minus 4 times rp plus xq. Right? Right. So now if we specify the turns ratio TS, if TS is specified, and from that you can calculate the TR because it could be equals to 1 over TS, right? But if we specify the TS, you can see that there's the square root of here that brings two values here, right? So you will have two values for v2 for given v1, right? There are two values for v2 for given v1, right? Okay, so let's talk about the so that conclude the step changing transformer part. So let's look at how the injection of reactive power can be used for voltage control. Right? Okay. So you know that the use of static capacitors to improve the power factor is established, and it's practicing all over the world, right? But okay, but when it comes to the reactive power or uh, the the reactive power uh, injection, right? The tap changing transformer is more cost effective than the reactive power injection method, right? So because of that, the reactive power injection is only used in the system where the transformer alone is not enough, right? uh, so let's consider the reactive power injection technique. So first let's consider the capacitive capacitance required for power factor improvement, right? So consider the capacitor required for power factor improvement, right? So let's say the the tariff is say, let's say the you have the tariff of the consumer be A times kVA plus B times kilowatt hour. So it's charged for the reactive power usages as well, right? So if the load of P1 kilowatt at power factor 5.1 lagging, right? So we have the reactive power drawn would be equals to P1 over cos phi 1, right? This is actually not the reactive power, this is the apparent power or the kVA rating, right? So this will give me the P1 over the kVA, right? So if the power factor is improved to phi 2, right? Sorry, the cos phi 2, we are talking about the power factor, not the angle. Okay, we can calculate the cost saving, right? So which is equals to A times P1 times 1 over cos phi 1 minus 1 over cos phi 2. I believe you are familiar with this calculation, right? So the reactive power required from correcting capacitor is equals to P1 tan phi 1 minus P2 tan phi 2 in kVA, right? So right, so this is the size of the power factor correction capacitor, right? So let's do some cost analysis. So let the cost per annum in interest and depreciation on capacitor installation be C per kVAR, right? So then the total cost would be C times P1 tan phi 1 minus P2 tan phi 2 per annum, right? Maybe in LKR or something like that, right? Right. So then we can calculate the net saving equals to you have the cost saving here, and then the cost for the capital interest payment and the depreciation of capacitor is here. So the net saving would be A times P1 1 over cos phi 1 minus 1 over cos phi 2. This is the saving done by reducing the reactive power minus the C times P1 Yeah, this should be as well as P1, right? If the same power is drawn. So this is tan phi 1 minus tan phi 2, right? So this would be the cost saving, right? And when you can find the maximum saving occurs, you can take the derivative of the net saving and equate it to 0, right? So by that you can find the maximum saving occurs when d over dt net saving is equal to 0. So then your sine phi would be equals to c over a. So yeah, you get the angle that you can improve the new angle to get the maximum saving, right? So you can see that the optimal power factor, there's no phi 1 here, so this optimal power factor where you get the maximum saving will only depend on it's independent of the initial power factor, right? Okay, but you can see that in this case this may not be equals to unity. In the power factor correction, in order to reduce the reactive power, the objective is to get the power factor closer to the unity. But if you look at the cost saving, you will end up with the non-unity power factor, right, which is the cost effective solution. So you will be limiting the power factor to non-unity, right? So the main effect of transmitting power at non-unity power factor are the voltage drop across the line will be increasing, and then the I squared R losses are increased, uh, so in turn reducing the thermal capability, right? Okay. Right. So you can inject the reactive power at the load end. Okay. There are 4 methods that you can use to inject the reactive power. The one is use the shunt capacitors or the static shunt capacitors. The other method is to use the static series capacitors. The third method would be using synchronous compensators. And the fourth method would be you can do the current compensation. by series injection, where you use the power electronic devices in order to inject the current, right? So let's look at these one by one in little detail, right? So the first one is the shunt capacitors and reactors. So if you want to supply the reactive power, you can use the capacitors, and if you want to absorb the reactive power, you can use the reactors. So capacitors are used for lagging power factor load, such as motors, right? And the reactors are used for leading power factor load. So example here are motors and pumps, and here the some of examples are lightly loaded cables. Right? So you can connect the capacitor directly to the bus bar or to the tertiary winding of the main transformer. Or the tertiary winding of a main transformer. Okay? So you can either, so you have the line and the loads and things like that. Let's say going to the load, so you can connect the capacitor bank directly to the bus bar, right? Or if you have a service transformer or something like that, so you can connect the capacitor bank to the tertiary winding of uh, the transformer, service transformer. Okay, so either way you can use that to get the reactive power support, right? So right, so I'm not just talking about the a factory or something, but even you can have this in a transmission line or distribution line, right? In order to give the reactive power support, right? But if you connect, you can see this characteristic is also there, right? So as the voltage drops, the VA produced by the shunt capacitor also falls. Capacitor is also falls. So I'm not talking about the power factor correction here. For the power factor correction, this would be okay, but in order to voltage control, right? I'm talking about that. So when the voltage drops in the line, and let's say you connected the capacitor banks somewhere in middle, the amount of reactive power that can be produced by the capacitor bank will also fall, right? So that is when they needed the most, their effectiveness is less. because we want to correct the voltage, right, let's say at this point, but the amount of reactive power that can be supplied by the capacitor also depend on the voltage. When the voltage drops, the capability drops, so the effectiveness is less when they actually require, right. uh, and on the light load, when the load is less, the capacitor output is large. I'm talking about the static capacitors here, right, large, and the voltage tends to rise excessive levels. Okay, so in that case you may have to remove some capacitors, right, or the reactance as needed, right. uh, so the solution is switched capacitors in parallel with semiconductor control reactors will help to solve this the problem, right. So this is provides the modern variable VAR compensators. Okay. So this can be used to control the voltage in power systems in a dynamic manner, right. Okay, so that's about the shunt capacitor, right. So you can use the combinations of shunt capacitors and reactance, right. uh, the next method is the series capacitors. Okay. So these capacitors are connected in series with the line conductors, okay, and are used in the reduce the inductive reactance between the supply point and the load. So you have the supply points here, and then in the line you have the line reactance, right, and so you can have a series capacitor, right, and then comes to the receiving end where the load is, right. uh, right. So you have XC, so you have I times XL current coming here, I times XC, right. So you can ready use to reduce the you can use this to reduce the inductive reactance between the supply point and the load end of the transmission line, right. So if you draw the phasor diagram, we will start from the receiving end. Let's say the voltage is VR and that's the current is IR or I, let's say. So you have the angle 5 here. So without the capacitor bank, you will have yeah, so let's say the R is negligible, and then you will have something like this, right. So this would be the Vs without the capacitor bank, without the capacitor, series capacitor, right. This would be the Vs. So this would be the Vs without the capacitor, right? And then uh, so this here would be I times XL, right? And now with the capacitor, now there will be a current in here, so this would be the new Vs. So this would be I times XL minus XC, because this is now compensating the effect, so you will get the Vs here without the with the capacitor. Okay, so you can use to mitigate the effect of the reactance of the transmission line by including a series capacitor, right? So one major problem here is that the high over voltage, right, that is produced when a short circuit current flows through the capacitor. When there's a short circuit happens here, the larger current will be going, and then there will be a high voltage produced through the capacitor, right? So you will need a special protection to accommodate such condition, right? So if you compare the shunt and series capacitor techniques, uh, so if the load, the VAR requirement is small, series capacitors are of little use, so you can go for shunt capacitors. Right? And with the series capacitors, the reduction of line current is small. Current is not going to change, right, much. So if there is a thermal consideration limiting the current, then again the shunt compensation would be much better compared to the series compensation, right? Rather than the series compensation, right? But if the voltage drop is the limiting factor, the series capacitors are effective. So this also remove the voltage fluctuation, right? Due to the like arc furnace, like loads. Okay. Uh, and series capacitance are very effective if the total line inductance is high. Capacitors are uh, very effective. Okay. Okay, so that's about the series and shunt capacitor arrangement in order to correct the voltage. Okay. Another method is to use the synchronous compensators. Okay. So as I said in the very beginning, these are basically synchronous motors running without mechanical load, right? So synchronous compensators are basically synchronous motors running without a mechanical load. Okay. And depending on the value of excitation, it can absorb or generate the reactive power. Okay. Uh, the advantage of this method is it's kind of a continuous thing, so you can continuously change the reactive power requirement. So other than like going for discrete levels in the capacitor bank, so you can so you have the flexibility of operating for all load conditions, right? But the one problem here is the cost of installation could be high, right? And the being a rotating machine, its stored energy is useful for riding through the transient disturbance. Stored energy in form of inertia is useful for riding through transient disturbance, including the voltage sags. Okay. And the final method is the series injection. of current by using a semiconductor device. So this use semiconductor device. Okay. So inverters are being designed and constructed that can inject the voltage in series with a line whose angle can have any desired relation with the phase voltage, right? The inverters are being designed and constructed that can inject the voltage in series with a line whose angle can have any desired relation with the phase voltage. So that means irrespective of the what is the angle at the line, you can use this to inject the current into the system, right? So you have, let's say you have the this VAs here, and you need to control the voltage at this point, right? And have the reactance, and this is the receiving end, and you have I minus 5 here. So you utilize the power electronics, right? And so you can control it, and there should be an energy source in order to support the current. Okay. And by using this method, you can control the injection of the reactive power. Okay. Okay, so with that we will conclude our discussion on the reactive power control, right? I will give you some questions to try, so I will upload them in the field so you can try before the exam, and I will also give you the kind of assignment or kind of a laboratory type assignments based on the automatic generation control, as I mentioned in the other video, right? So I will upload it to the other fields and you can work on that. Okay. Thank you very much.